Good afternoon. It's 2 p.m. I think we can start the session. So welcome all of you to the session Network Control and Management. My name is Bartosz Belter. I'm from Poznan Supercomputing and Networking Center, and I will be chair of this session. Today we'll be hearing on some control and management aspects from the academia perspective. We'll hear about the end customer experiences with AutoBAHN deployment. We'll hear some research results about Ethernet fault management across multiple domains. But the first talk will be from the industrial perspective. Michael Beringer from Cisco, France. He will be talking on managing network complexity through autonomic networking. So, please.
Test. So I'm just getting set up here. I do expect this talk to be somewhat controversial, so I'm just getting ready. This is about autonomic networking. Some of you have already heard my presentations about complexity. It takes this one step further. Where am I coming from? I'm working with our customer base on infrastructure security protection. So basically, if you have a critical infrastructure, your network, how to protect that. Turns out that is a very difficult task. And while working with our customers to solve their problems, to make that manageable, you sort of realize, this is not going the right direction. It's getting more and more complicated every single day. And so there I started thinking, this is not right. We need to do something about that. And first I started looking at what is that complexity, and now I've started a project together with a few colleagues on actually how to solve the problem. And this is what we are presenting today. I say it will be somewhat controversial because I don't think many will be used to thoughts like, you do actually not need humans to configure networks. They can configure themselves. And that is what this is all about. So let's start on the complexity side. When I look into the security aspects of network, of protecting an infrastructure, we go through all the measures that you need to do to protect just the infrastructures, the routers, the switches, and so on. And it gets enormously complicated. And I claim to say that there is probably not a single network out there in the world that is really optimally protected. And frankly, it's almost impossible. And why is that so? Because we add more and more features to our things, to our routers, to our switches. The service provider or the enterprise also adds more and more stuff, more routers. Those more features translate in more lines per configuration. What you see on this graph on the left-hand side is taken from a tier 2 service provider in Europe. So you see at the bottom line the growth in the number of routers. You see on the top one the growth in the numbers of lines of config per router. That doesn't look good. On the right-hand side, you see the image size evolution of one of our particular operating system trains. And you can take whichever, they all show that tendency. And if you ever thought that Cisco is bad at putting features into code, my God, are we bad at pulling things out of code. Right? Much more difficult to get stuff out of code once it's in there. So also there you have this curve increasing, more. And if I look at this and other statistics, I come to a very simple conclusion. In a few years' time, we will just not be able to configure networks the way we do today. As simple as that. We need a new approach. The way we manage networks today is not scalable. And so first I had a look at the problem space, at the complexity itself. And to frame my own thoughts, I came up with this complexity cube, where I essentially locate where you have complexity. And give you an example. Routing, for example, is a function that is typically in the physical network, in the bottom left corner of this cube, because it's part of the operating system of each router. Routing can also be dealt with on the operator side, on the human side, if you want, because you could theoretically derive all your routing information, put a lot of static routes into your network, and do it that way. Nobody does that, thankfully, or Not yet. Let's see where we're going. This is one way to go. We have also quite a few different approaches. But clearly that is another way of doing routing. And of course there's the third part of doing routing that is very much under discussion, especially in this community, because with OpenFlow essentially you outsource routing to a central entity and you just update the forwarding tables in the device. So the intelligence really is in the third party, in the centralized system, right? Which is not part of the actual network. And so when you look at that, there are a few things that are immediately obvious. If you are working on running networks, it is immediately obvious, really, that you need to reduce the complexity on the operator side. 70–80% of outages are caused by human error. What do you want? Right? Many service providers are pretty clear about that, say, I don't let any human touch my network unless it really, really is necessary. Not many go quite as far, but the general philosophy, I think, is widely accepted. Human error is still the biggest problem we have out there. But then there's the other part, and that's the central elements, the big NMS systems that manage everything. And I claim we have another goal here, and that is to reduce the dependencies here. And what do I mean with that? In order for a central system in today's world to configure and manage a network of diverse devices, potentially multi-vendor, certainly multi-platform, very certainly multi-operating system versions, the central entity has to understand every nut and bolt of every single device out there. That is a dependency because that entity, that central brain, is dependent on all of the operating system versions out there. And you know very well what that means from your day job. If you swap out a piece of equipment at the bottom of your network somewhere, it has a huge dependency on the central element there. And actually this is, now, if you combine those two things, this is what autonomic networking really is all about. It is about minimizing the dependencies on the human operator, on the person who is configuring. And it's about minimizing the dependency on a central entity. So in a way, it is sort of 180 degrees from OpenFlow, for example, where you try to centralize everything. Now this sounds new. It is actually not. Right? This has been around for a long time. And if you look at routing itself, for example, look at OSPF, ISIS, whichever of the IGPs, those are essentially, in my definition, autonomic processes. Why are they autonomic? Because for that process, nobody needs to tell the router what to do. It just says, you route, bottom line, right? But it's the router that does the work. It talks to the elements around it and is trying to figure out what the network looks like. And they talk, and they talk, and then they talk all back, and after a few milliseconds, you have a converged view. There was no central intelligence involved. Right? That is a truly autonomic process. And you know what? We're just taking that one step further. Because not only routing, everything can work this way. And so I said it's not new. IBM actually more than 10 years ago has defined the properties of self-managing systems. And they have defined all these self-properties, self-managing, self-healing, self-optimizing, self-protecting for sure, and so on. So we're just building on top of that, because that is a system-based view. We are really taking the network view. There's related work going on in the ETSI right now, and there's the general autonomic network architecture, the GANA architecture, that actually also tries to solve the same problem. That's related work in this space. So if you look at what we do today in most of networks, you have a very, very strong northbound interface in your network. Because a router, a switch, a whatever, will not do anything until somebody has told it pretty much manually in a long config what precisely to do. The east and westbound interfaces in today's network are pretty slim. We do routing there for sure, which, as I said, is an autonomic function already available today, but that's about it. So without this strong dependency on the central element, there's nothing working in a traditional network. In an autonomic network, that is slightly different. We try to minimize the northbound interface. And I say minimize because I'll explain in a second, you can't get rid of it completely for a number of reasons. But you can reduce it dramatically, believe me that. And we have actually prototype code that shows exactly that. So we do not, in this northbound interface, if you look at it, we do not look at config at all. Config in the autonomic process is gone. There's no such thing. Therefore, the human will not be actually interfacing configuration at all anymore. I should also add at this point, by the way, obviously this is a vision, right? It'll take us a couple of years to get there, for sure. So bear with us while we're working on it. Not all of this is doable right here and now. But we have enough prototyping going on to be able to say relatively boldly that this will work. So intent, what we call intent, is essentially a high-level policy. And just to give you an example, in a network, intent would be this network has guestnet. Or this network uses IP prefix X. That's it. Nothing about who uses which part of that, how it is distributed. Let the network figure that out. Right? So intent is a type of policy language, but on a very abstract level, very high-level abstract level. It does not allow you to address a particular element in the network. You cannot. It has a network-wide scope. You say, this network has guestnet. Locally, the devices need to translate that in what it means to them and take the appropriate steps. And of course, that makes the east and westbound interfaces much, much more heavy, much more important. Imagine like routing on steroids. Routing, but exchanging much more information in the same autonomic fashion. In other words, neighbors talk to each other. They figure out what they need to do independently of what the northbound guy, the operator, is telling them. There's, of course, also reporting in this model, has to be. There will be feedback loops. So, obviously, also in an autonomic network, the operator wants to know the state the network is in. It wants to be informed about problems there are. We believe we can also there change that massively such that you do not get, when a line goes down, 20 syslocks that all have the same root cores, but for each layer in the stack you get a different syslock, but you get one saying link down. So a lot of the processing also here can be done in the network before it is actually passed on to the user. So looking at the traditional network, this happens today when you plug together a network and it's not configured yet. Nothing. In a traditional network, you have a massive dependency on a central brain. That could be you, the guy typing it all in, guy or girl, typing it all in. It could be, in most cases, it is some form of a network management system. Again, strong northbound interface. You have, most importantly, you have a connection to every single device out there. An autonomic network works slightly differently. And the way we see this working, and that is now our interpretation of the whole story, there is still the device operating system, and that will not change. So we will not reinvent routing or failover mechanisms or what have you. But we will configure them automatically. So there is, imagine, on top of the operating system, there is a process, an autonomic process, that actually does this processing. And it'll figure out, hey, there's a neighbor. It'll figure out, I'm from the domain terena.org. Talk to a neighbor, which domain are you from? And it'll say, I'm also from terena.org. I'm a router, what are you? I'm a router too. You know what? We should probably route. Not really rocket science, is it? And from there you extrapolate. We have a prototype that does exactly what you see on this slide. You plug routers together randomly. It doesn't matter which cable goes into which port, because it's all discovered dynamically anyway. You need a strong device identity. This will be a domain certificate, so you need to prove who you are. And after that, a lot of the rest falls out automatically, pretty much as by magic. There's no rocket science in there at all. So I talk to my neighbors, I figure out same domain. Okay, same thing, so we start routing. Now you'll ask, so will you start OSPF routing and or ISIS or whatever else? And ask you back, do you really care? And I know in this particular group, many of you will say, yes, I do. But why do you say that? Because today you have to actually do all the configuration yourself. You have to do it yourself. You have to know what you're doing. So you do the stuff that you know, of course. Okay. Now, you will spot within 2 nanoseconds what the problem here is. Without any northbound interface, take a simple case, how should the network figure out which IP prefix to use? And the answer is, it cannot. Well, okay, you could imagine prefix delegation maybe from the edge, but let's say for a moment we cannot. There are things that the network cannot figure out itself. That's, I think, the key observation. And for that, we have a higher level concept that is called intent. I already explained roughly what it is. So it is very high level policy that has a network-wide scope. And a network-wide scope means you cannot address intent to any particular element. It's always the network does, the network will do. You can say the routers in the network do, or the edge elements in the network will do. That, yes. But you cannot say router 17 over there, up there. No, you cannot do that. Now, if you take this level of abstraction, there's something really elegant happening. Actually, you don't need to worry about an 1 to n connectivity into your network to manage it. No. You can actually wrap this intent into a file. We believe this file will be very small. A few dozen lines maybe, not big, because it's very high level. And you just shove that into the network in a particular point. The element you're next to at this point in time. Doesn't matter which one. And it is the job of that element to actually flood that intent throughout the network. So now the entire network sees the intent of the operator. It translates that intent to what it needs to do. And now comes the step where configuration comes in, but it's on the element, it's not up there. And it translates that into, call it a configuration for now, because we know what that means. Also important to say, we're not trying to reinvent the wheel here. All of the traditional interactions, routing, failover, and the like, we just use whatever we use today. So it's not about reinventing networking from scratch. It's just a different way of enabling it in a way. And now the intent will also tell me, for example, what I need to do at the edge of the network. Important, the PC here on the left-hand side, in many organizations, that is considered as inside the network. In our model, it isn't. It's not part of the network. It could be, by the way, could be, but traditionally it shouldn't be part of the network. Therefore, the edge element over there will wait for the intent to know what to do with this PC or router or whatever. That's a policy question, right? And again, you can set a default, right? But there needs to be a way for an operator to set that. Now, let me summarize quickly, and obviously, in 20 minutes, I cannot go into a whole lot of detail. I can only give you the high-level view. In a summary, autonomic networking to me means that each element configures and manages itself. It is not dependent or minimally dependent on somebody sitting up there in a NOC and pushing any button. The dependency that we do have is on, what I said, intent, high-level policy. There will be feedback loops where this operator gets asked, I see the following condition, I suggest we should do X. What do you want to do? There will be some form of aggregated reporting for sure. But the emphasis in the whole approach is on the east and west bound. Every network element figures out itself what to do. And so with that, I already want to finish because I do want to leave time for questions. I hope that there are lots of questions. And I just want to acknowledge the work of my colleagues. This is not my work. We are actually a fairly sizable team by now working on this to make it happen. So this is really a team effort, and my contact email is up there. Thank you.
So thank you, Michael. Now it's time for questions. Are there any questions? Please wait for microphone because we are streaming this too.
Yeah, hi.
Hello. Most of the things that you just told, I'm already seeing with a big competitor of you, Burkett, with their VDX line. So it's not really sounding very new.
I told you it's actually not new.
No.
However, there is practically nothing in reality running out there.
I can buy the stuff now if I want to.
Okay.
The only part that they're missing is the layer 3 part, but I know that they're going to launch this summer. So.
Okay, thank you.
Hi. What will be the role of traffic engineering in that model? Do you have to do it anymore?
What will the role of cloud engineering?
What will be the role of traffic engineering in that model? Do you have to do it anymore?
Now, let's be honest here, right? We are also in the process of figuring this out. So the answer I'm going to give you is brainstorming. And I invite you all to brainstorm with us on that, because to a large extent that is still research. Right? But I think a lot of traffic engineering you could automate. Right? You can see on a network where traffic is going, where there's an overload. You can negotiate back, saying on this link is an overload. Ramp up the costs automatically. I don't think that is rocket science. Will we go for that in the next 6 months? For sure not, right? Also because people will not be willing to use a system like that, a completely novel system, and run it in their production network from day one, right? So what we are doing right now is not actually developing the full vision here, because nobody's going to deploy that right now. But we are trying to package it into small autonomic functionalities and try to get step by step, have some progress. Look at what's going on your car, right? Who is still operating the light switch on his car, right? I'm not, right? In my car, the light switch is on and off automatically. The windscreen wipers, also in my car, I do nothing. If it starts raining, the windscreen wiper starts going. This is autonomic functionality, and it's coming into cars step by step. There is also the autonomous car. You may have heard that from Google, right? That's completely automatic and runs completely autonomically. Yes, that will come as well, but it's a little bit further out. We have the same thing here, right? So the long vision is further out, but small steps of autonomic functionality we can implement pretty quickly. There's a question over there.
Hi. It sounds a good idea, but when you think of an intent translating into configuration lines, at some point there's going to be a translation, but at the end, there's human behind the machine shooting intent commands, right? So this group of people should know what it translates to in terms of configuration. Does it make sense?
I see what you're saying. I don't think so. And so, but again, this is an adaptation curve. This is not going to happen in one step, because obviously if I tell you our network configures itself, go home and sleep well, you're not going to buy that, right? It's quite clear. But at the same time, I think we can automate a whole lot of function without you needing to bother. And my favorite example is the choice of routing protocol, right? How many discussions have we in this community around this subject? And I ask you, okay, take your network and it runs with routing protocol A. Will you get it working with routing protocol B? And the answer, if you're honest with yourself, is of course, right? Pick the other one of the two big ones, right? Of course you will. Is it going to have any significant difference? Probably not. You choose it because you know it, by and large. So I think a lot of the discussion we have today are really not necessary anymore. We can pick one, we can optimize one. Right? And I don't think that the operator really needs to know all the details of that. And again, this community is somewhat special, right? Let's also not forget that. You guys want to play, you want to learn. It's somewhat special. But think of an enterprise. Many enterprises, the network is a commodity. It needs to run. They don't care.
Thank you.
Just a remark, comment to your presentation. Are you also analyzing the business implications of your approach? Are you trying to minimize or change the role of network operators in this approach? Because it looks to me it's to make their life easier. So are you trying to solve these problems as well from the business perspective?
It is the goal, of course it is. And again, back to where I'm coming from, right? I'm trying to help people to secure their networks. Now, observation number one, securing the network itself has absolutely zero business benefit to the customer. They have to do it, they realize it, but they hate it because they have to put a lot of effort in and there's no revenue attached to it. It just means the network keeps running. Well, that's not particularly interesting in a business. So yes, we are trying to essentially take out the commodity, if you want, of configuration and put that into the network in a prepackaged format so that it just runs on its own.
So,
any more
other
questions?
comments?
Well, am I here? There's a question down here.
I just wonder how this will solve the current scalability problems that you anyway have already in your IP networks. How it will work in multi-vendor environments and how it will work in multi-layer environments, which are becoming more and more important.
So this is an architectural approach. We will take that to standardization. The multi-vendor can be dealt with. There's no rocket science here, right? There are some additional protocol. I don't think we need 1,000. 200 should do.
No, 200 is too less.
No, actually, if you look behind the scenes of that, it is not rocket science, right? A lot of that stuff is actually fairly simple. Because, again, we are not reinventing routing. We are just enabling, we are just configuring it in quotes, right? So this is not as complicated as it seems.
I do agree, we need more abstraction, but the question is, where do we need more abstraction? Yeah, so this is my topic, which I have. In principle, I agree. That's not rocket science because it's just carrying the control plane approach a bit further. So therefore, it's not rocket science. And of course, you can implement it within Cisco easily. That's for sure. Yeah. So, but doing it multi-vendor and also tackling the problems which I just mentioned is a little bit more difficult because it's not just one company out there.
Yeah, absolutely, and this has the typical standardization problem. How many years did it take to get anything MPLS standardized, right? It was a huge thing. I don't mean to compare, by the way, but yes, this will take time. Of course it will. And it will take time also because a number of things like traffic engineering need to be worked out. But hey, this is where you guys come in, right? Now we just need to switch our thinking a slight bit. And rather than thinking, I have this central algorithm that does everything for me, can we not solve this in a distributed fashion? And I believe we can solve a lot of things in a distributed fashion very, very elegantly. Right? And that then has the abstraction factor automatically built in. I didn't hear that, sorry. By the right abstraction, exactly. Any more questions? Then thanks for your interest, and I hope to hear from you.
Thank you. Thank you very much.
Thank you.
So now it's time for the second speaker, Freek Dijkstra from Sarah, Netherlands. He's currently working in Sarah, where he develops standards and software for innovation networks. His interests are topology descriptions and monitoring of multi-layer and multi-domain networks. So Freek, welcome.
Thank you very much. My name is indeed Freek Dijkstra. I work for SAR, the Dutch supercomputing center. Is it on? Yeah. for the Dutch National Supercomputing Center. I did this work with a few colleagues of mine, and this is actually me in Iceland about 29 years ago. And what I was doing here is counting waterfalls. And about this time, I figured out that this is a big problem. But fortunately, in about 29 years ago, not much has changed, because today I will also do some enumeration, which is about open issues in Ethernet OEM. If you deploy Ethernet OEM in a multi-domain environment. About fall last year, at Supercomputing 2011, a few colleagues of mine, including Ronald van der Pol, Sander Boele, and myself, as well as a few partners at CRC and iCare in the United States, did a demonstration at Supercomputing. It was basically an OpenFlow demonstration, but for the monitoring, we used Ethernet OEM. What we did, we created a few Ethernet VLANs, mostly across the world. And that's actually what a few environments are doing these days, the light paths. And these light paths are typically implemented as VLANs. And you like to monitor them. You like to know if there's a problem, where is the problem? So fault isolation. And Ethernet OEM is actually a set of protocols to help with that. Ethernet OEM, or Ethernet CFM, is actually two names for more or less the same beast. It is not one, but in fact two standardization organizations which defined the Ethernet OEM messages. On one hand, the IEEE did their standardization in the standard 802.1 AG. They called it Connectivity Fault Management. And on the other hand, the ITU did some similar work, and they standardized in I-1731, and they called it Ethernet Operations Administration and Maintenance OEM. The standards are comparable for the connectivity message. There will be three messages. I will go in a bit detail in a few moments. The ITU standard, in addition, added a few performance messages, and that's basically alarms, remote fault messages, indication, RFIs, which are not present in the IEEE standard. I will use a few terminologies. Ethernet OEM, Ethernet CFM are both basically the same thing, but I will use some additional terminologies which are common in this standard, which is a MAP, which is a maintenance endpoint, which you can think about as a monitoring endpoint, a MIP, which is a monitoring intermediate point, and MAAD, which is the maintenance association identifier, but you can think of it as a domain identifier. The MD level, I come back to that. It's basically the scope of the link you want to monitor. Are you going to monitor just a small link, or are you going to monitor the end-to-end path? And the map identifier, well, that speaks for itself. So 802.1 AG as well as Y1731 defines a few messages, and the messages defined for connectivity are the loopback message, the link trace message, and the continuity check message. Loopback is actually two messages, the loopback message and the loopback reply. And you can think of that as a layer 2 Ethernet ping message. So you send out a ping message, and you get a loopback request back. So it's unicasted to a specific MAC address, and you get a reply. So it's just layer 2 ping. Link trace is more like layer 2 trace route. You send out a message, and every MIP along the way, every maintenance intermediate point along the way replies. So you know what the route is that your Ethernet message takes. That's actually broadcasted, not unicasted, because the destination, of course, is a specific MAC address. But you don't want only that MAC address to reply, but also all the MIPs along the way. So it's actually broadcasted with the destination MAC address somewhere hidden in the body. The continuity check is a different beast. It's a one-way hello. Rather than being a request and reply message, it's just a one-way broadcast message saying, hello, I'm here. And everyone who receives that message knows, okay, that machine can reach me. So it's a way to check for link status, if the link is up, it's reachable. Well, when we deployed this last year, we found out that if you deployed an inter-domain situation, you will have to make a lot of choices, like every protocol you are going to deploy. And because you deploy that not within your own network, but across a number of networks, you have to agree on a few things. And this is a list of open issues that you have to agree on. And I will go through the list in the next few slides. The first thing you'll have to do is decide what type of message you're going to use. I'll confine myself to the Ethernet OEM messages, the 802.1 AG messages. So that's the link trace, the loopback, and the continue check message. And of these three, we think that the continue check message as well as the link trace message are very useful to use. The continue check message is very useful for link status tests. Typically, it's done automatically. It can be configured in a host that sends out, for example, every second, a continue check message to all their neighbors. Every neighbor then knows, okay, this host is still reachable, unless after it misses 3 of these messages, it knows, okay, now this link is down. That's really useful for automated tests. However, if that link is then down, what you typically like to do as a network engineer, or perhaps automated, according to the previous speaker, is then, okay, where is the fault? Where exactly, which segment of my path is down? And for that, the continue check message is not very suitable, but rather you like to use link trace messages. So we think that these two messages are useful to be deployed in an inter-domain environment, like the NRENs we have here in this room. The next question is, okay, who is going to deploy that? We think that typically the continue checks message are an automated test tool which will be deployed by NRENs. On the other hand, the link traces will be deployed by both NRENs and, if possible, end sites like campus networks also like to know where the problem is if they are the end of an end-to-end VLAN, an end-to-end light path. If possible, because sometimes a light path does not terminate at an end host, but rather a router at an end site. For example, at SAR, we have multiple light paths coming in, and each of these, the data of these light paths like to use our storage system, likes to use our computing cluster, rather than terminating all that at the end host. That's not very scalable, because then you have a layer 2 environment which you need to use all the same IP addresses, which doesn't work, obviously. So we have a router in between there. But sometimes the end user does not have access to that router to start a link trace message. So you actually also like to have some out-of-band system where the user can initiate such a link trace message or fetch the results of continue check messages from that router, rather than having full access to that router. So there is need here for some kind of a northbound interface, in fact. Another question which we are facing is, okay, typically these end-to-end network connections grow to multiple NRENs. And sometimes the boundary between those NRENs is a light path exchange, like a CLIF open light path exchange, a goal. The NRENs then have a choice. Are they either going to provide some transparent circuit to the end user, or are they going to, in fact, add also this monitoring to the circuit of the end user? The difference is that if they provide a transparent internet tunnel, basically, data comes in and data comes out. They don't change it, which is typically very useful for a lot of protocols because, well, it just comes in, goes out, which is what most users like to see. But for monitoring, it's not really useful because if something comes in and nothing scatters out, well, you have a problem. You don't know where the problem is. So the question is whether or not the NRENs like to deploy MIPS, dus the maintenance intermediate points, at that light path. The advantage is that then the user can actually see, can do a link trace route and see where the problem lies. On the other hand, you can also say, well, that's not really necessary. You just put a measurement intermediate point at the beginning of your network and at the end of the network at the edge. And the user makes a link trace And if there's a problem, you know, okay, it's in this network. I don't know exactly where in this network. I'll just know who to call, my NREN, and he can figure out exactly where the problem is. That's a decision to make. Our gut feeling is that the measurement intermediate points should at least be at the exchanges, at the boundary between domains. Whether or not the NRENs should deploy more measurement intermediate points within their network, that's an open question. And I think that, in fact, NRENs will make different decisions about that. And that's okay. Okay, and there are actually two harder problems which are related to how the protocol was defined. The protocol, if I look at it at least, it's really defined for deployment in a single domain. One of the things that it says, it rather than an IP ping or an IP trace route, you just do a ping and you get a reply back, regardless whether that destination is a host in domain A or domain B. For Ethernet OEM, that's not the case. An end host will only reply if the maintenance association identifier, that's that MID, the domain identifier, is the same as the domain identifier from the request. So if you're sending something with a domain identifier, MID, from your domain to another domain, which has a different MID, it doesn't reply. So that's not very useful for inter-domain monitoring. So the MID has to be the same for communication to occur with Ethernet OEM. Well, how does this MID look like? In fact, in the standard, it consists of two parts, an optional domain name and a short name. And that domain name can take different forms. Well, it's really standard, so there's a lot to choose from. It can be a domain name string, a MAC address plus an integer, or just a random string. Well, not random string, but a string without predefined syntax. That's optional, so probably in this community, we will probably have to decide that every NREN has to use the same MID. That's unfortunately, but that's the case if we like to communicate and deploy Ethernet OEM interdomain. For the short name, you have to decide on something. A typical choice would be to use the VLAN ID, which is great because you can use just a VLAN ID depending on the link you're using or the VLAN which is configured. Unfortunately, that's not really very useful anymore with the uptake of VLAN translations, which a lot of NRENs are deploying nowadays. So that doesn't work. So I think at our demonstration we use something like Cliff demo as the domain identifier, but you have to decide that for every single link. That doesn't seem very useful to communicate that in advance. So our feeling is that we probably have to use something like an empty string or something, so that at least you know if I'm going to send a link trace request, I get a link trace reply back. Another thing to decide upon is the MD level. This is basically the scope. As I said, are you going to measure a link segment or the end-to-end path? The standard allows you to set a bit, which is 3 bits, I think, which is MD level, and on what they define, they specify that at the lowest layer you have a lower MD level, and the higher layer you have a higher MD level. So what happens if I send out a packet with a MD level of 1 and it encounters a map of layer MD level 2, it blocks. So the scope of that packet is really depending on the MD level. If I encounter a map which has a higher MD level, it blocks all the packets of that level and lower. So here's a picture how it, for example, could look like. I have here an MD level of 2, 4, and 5. So the MD level of 2 only measures shorter paths than the end-to-end, on the higher MD levels. So we have to decide upon an MD level. And we have to decide on a different MD level for continue check messages and for the link trace messages for the following reason. As I explained, that the continuity check messages are only between two maps. Well, I don't think I mentioned it before. They're between two maps. On the other hand, the link trace messages are in the end between two maps, but the MIPS in between the intermediate points also reply. They don't do that for the continuity check messages. So you need a lower MD level for the continuity check messages than for the link trace messages. In our experiment, we used level 4 for the continuity check messages and level 5 for the link trace messages. But we have to agree on that if we want to exchange Internet OEM data. And again, we think it's useful to agree on for once and for all, rather than for each specific link, because then you really have to negotiate it again and again and again. It's of course possible, and if you like to deviate from whatever we agree on, perfectly fine. But then you have to agree on it beforehand. Another issue is how to define your endpoints. It's really great that I can do a ping or a layer 2 trace out, a link trace, but if I get a reply, okay, this and this MAC address are reachable, what does that say to me? I don't know what your MAC addresses in your network are. So we need to find some mapping between the identifiers in your domain, which are for the link traces and the loopback messages are the MAC addresses, and for the continuity check messages, you not only get the MAC address back, but also a map identifier. That map identifier is a 13-bit integer, really weird number. So you can have as much or as few as 8,000 different maps on your VLAN. That's not very much. Definitely it's not enough to make the map ID globally unique. So you have to agree on a map ID for each and every link, every VLAN. And that means you need some coordination to prevent collisions between that map ID. How we did that previously, we just said, okay, this range of map IDs is for this partner, this range is for that partner, and this range is for that partner. But you can distribute it globally. It works, of course, very well for our small VLAN with only a few domains involved. But we don't see an alternative than to do some out-of-band coordination to prevent those collisions. That's unfortunately, and that's a consequence of the protocol. We can try to change the protocol, obviously, and in fact, my colleague Ronald van der Pol had an open source implementation, and you can add another TLV, type length value attribute, which has a longer identifier. That's great, but that's not supported, of course, by a lot of the other implementations. And still, it doesn't solve the problem that you can have a map, a collision between map IDs. So what do? Either you do some out-of-band coordination for the map ID assignment, you accept collisions and you use the MAC addresses for identification, or you use some DNS name or URN in a protocol extension. We don't know the solution right now. If we talk to most partners, they think that out-of-band coordination between map ID assignment for every VLAN is the best way. We are more inclined to look into the last option, but that has to be agreed upon, and some implementations and some more experience will hopefully solve this. The last item is actually a simple one. If we are going to deploy continuity checks, we have to use a specific time interval. You can actually change that for every VLAN. We would recommend to just use one message every second. Actually, the protocol specifies a few options. It also says it's embedded how often a continuity check message is sent within every message. So if a MIP receives a message, it knows, okay, I'm expecting the next message in several milliseconds or so many seconds. So then it knows, okay, if I don't receive that message in so many times, probably the link is down. And one message every second seems fine-grained enough for inter-domain monitoring. And that's it for the issues we found. If you have questions, if you have discussions, if you have other opinions, please bring it on.
Thank you, Frick, for your presentation. Are there any questions from the audience? Okay.
I have a question for the audience then. How many of you did implement Ethernet OEM or are experimenting with it by now? Okay, that's a few.
My question to you is then, I'm pretty sure you are aware of Personar. What Personar is, the joint effort of Internet to GEANT community. Are you aware if Personar is trying to take a closer look at the work you are doing? I understand this is the proof of concept for some networks. You did a demo, but did they start some work in this direction?
In fact, we used Persona last year for demonstrations. It was a really quick hack. I won't show you the message format because it's really ugly, but it worked for us. What we did, we measured, we sent out continuity checks to every point, and at every point we measured which other maps where we received continuity checks from. That we put in some RRD database, and that RD database was made available using Personar.
Is there an interest from NRANs to deploy such tool and run it in production?
There's definitely interest to run Ethernet OEM because it's very useful for monitoring, either automatic or manually with the link traces. I think there's still some open questions how exactly we're going to tune the parameters there.
Yeah, there is a question from audience, please.
Yeah, Freek. I was just wondering about how this would work in a real world environment where we have multiple technology layers. This is kind of focused solely on Ethernet, and there are some serious issues with Ethernet in terms of these switching technologies, right? Is this something that is really necessary for a multi-domain environment, and how does that map to, or what are the prospects for it in a multi-layer virtualized environment?
Well, the good news is that we see some other hourglass forming, and that we have some IP services that NRANs provide, and for the end-to-end links between domains, we see that they're mostly converging on VLANs. So you can actually monitor those VLANs. And if you like to hook that up to some measurements on either lower layers or the IP layer, yeah, that's perfectly fine. But then you need some topology model, and I can talk to you about that too, but that's a different discussion.
Thank you.
Another question?
Would you use this technology to monitor your company or campus network? For example, your desktop switches and such, to see if end-to-end from any desktop to any other machine in your network?
You can definitely use it to monitor your campus network. In fact, that's one of the use cases for this protocol. At least I can't look into the heads of the people who defined this protocol, but to me it seems like a great example. If you're going to measure also your end host, it's a different question. Yes, it's technically possible if you implement Ethernet OEM also at the end hosts. And in fact, my colleague Ron van der Pol made an open source implementation which you can install on end hosts specifically. So yes, you can. If you want to do that, that's a different question. So I think that most end hosts also speak IP, and you can also do some IP monitoring these days. So why add some other monitoring?
Do you see this technology becoming standards over, let's say, 5 years in switches, routers?
No, in 1 year or now.
Okay.
If you buy a new switch these days, if you pick the right one, it definitely has Ethernet OEM capabilities already.
Thank you.
Are there any questions? If not, thank you, Freek, for your presentation. And we have the last speaker in this session, Bruno Heft from Karlsruhe Institute of Technology. He joined as an engineer in 1989, the Karlsruhe Institute. An interesting fact from the history is that from 1994 till 2002, he was on the social purposes on a leave of absence, and during this time he supported Nepal in medical mission organization in the setup of the IT infrastructure. Now he's back in Karlsruhe, and he is responsible for the design of network of the German LHC Tier 1 Center. He will be talking on end customer experiences from the AutoBAHN deployment. Okay, Bruno is almost ready to talk.
Still fighting with the technique.
Okay, the floor is yours.
Thank you. Okay, hello, thanks for the introduction. Oops, okay. I've written this talk together with from my side, I have not to say anymore. So I'm from KIT, Karlsruhe Institute of Technology in Germany. I've written this talk together with Kostas Stamos and Tanguy Koloran. This is about an AutoBAHN testbed. The title is slightly misleading. It is not an standalone AutoBAHN deployment for this AutoKNF testbed. This is more the use of the current AutoBAHN deployment of GEANT. The agenda is has three parts. The first part is a little bit about the AutoBAHN history and the further development towards the bandwidth on demand activities. Then it's about this AutoKNF project, a small sketch about the infrastructure. Then I have in there a few slides of how to reserve the how the dynamic circuit reservation is taking place, or what's all about this. And then I will show one obstacle we found during the length of our AutoBAHN KNF project, and I will show you some real results we had during having this dynamic circuit running, and then finally at the end a conclusion. Okay, a little bit about the AutoBAHN history. This was deployed in the GEANT 2 project and was envisioned as a multi-domain environment of European entrants, and it should have the ability to be applicable in a under several technologies and in a multi-vendor environment. The most AutoBAHN implementations currently in the European environment, but recently there is one optical burst switching network in Ireland which has applied AutoBAHN. This is exemplar. AutoBAHN is further developed in the GEANT project to support the tool-agnostic multi-domain bandwidth on-demand service. At the contrast to AutoBAHN, the bandwidth on-demand service includes a much wider area of different aspects, like procedures within the service as well as the border areas, like time service, calendar, reservation, and it includes a much more mature and significant monitoring environment, as well as public relations and marketing, and it needs a cost-sharing model for getting the different partners together for financing the infrastructure, and last but not least, an authentication and authorization infrastructure. Besides this, bandwidth on demand is a tool-agnostic service and does not support only the provisioning tool AutoBAHN. It supports also OSCAR, OpenNSA, and OpenDirect. These tools are integrated via IDCP, the Interdomain Controller Protocol. Currently, there are named the European entrants, which are all involved within the AutoBAHN project and which are all participants. This is just a snapshot of the list, and there are still European participants welcome to this project. The AutoBAHN tool itself has, if we come here from the top, it's a user interface where a user approaches the domain manager for reserving a dynamic circuit. Then the domain manager has two interfaces. One is to a neighboring interdomain manager via the lookup service, and then to this domain manager of his own domain. If a user comes with a request for a dynamic circuit, the interdomain manager is first talking to his domain manager, and then the domain manager is looking through the technology proxy to his data plane and checks out if his data plane is able to fulfill the request. And the data plane are currently three possibilities. One is an interdomain. One is an IP domain. The IP domain is based on a layer 2 MPLS VPN, and it could be that it's an SDH domain, which provides the circuit via a generic framing procedure, or it could be a general Ethernet domain, which is just native Ethernet, where are then the circuits built over. So if a user request from there is able to be fulfilled within one domain, then the domain manager, then this is done within this domain. If the request cannot be fulfilled within one domain, then the interdomain manager is talking to his neighboring domain till the circuit is built and ready. The one part which is quite essential, at least in the European environment, this was the development of CNIS. This is the Common Network Information Service. This is the software tool which bridges between the NRAN. Every NRAN is very reluctant in opening their infrastructure to other parties. So the aim of CNIS was to provide a unified repository of all relevant network informations about a single administrative domain. So CNIS was expected to be a single point of storage of an automatically collected infrastructure repository of NRAN resources. But in fact, it is more than just a database. Apart from the international functionality required for populating, validating, and updating the database, it is equipped with modules of analyzing the topology data and presenting the data in a client-specific format. This client-specific format can be graphical, or can be in a tabular form, or even in an XML format for external applications. CNIS is further equipped with the functionality to share the infrastructure information abstract across NRANs without validating the confidentiality of an NRAN. So this is now about the AutoKNF, the bandwidth on this is a bandwidth on demand project, and AutoKNF stands for AutoBAHN, and the first K is for Karlsruhe Institute of Technology, N is for Nordernet, and F, Fermilab. These were the three envisioned collaborating partners within this project, but currently there is only the K for Karlsruhe Institute of Technology and N for Nordernet. If we will cross the transatlantic, we will see. So, and the other part which I mentioned there, the establishment of AutoBAHN-based circuit will be told in the slides, and I will go through the reservation handling, like I mentioned in the beginning, and will go then into the findings what we had during the dynamic circuits was up and running. A little bit of the history of the project AutoKNF. We had already some talks about the project in 2009 while the GEANT 3 was opened, and we could win in 2010 Nordernet to join the project, but it took till to the end of 2010 since we had the somehow the status that we thought we could take all the different parts together to light up a dynamic circuit. This is the infrastructure we have currently in the AutoKNF project. This starts there in Nordernet, where they offered a host to the project, and then we have a static infrastructure from Nordernet to all the way down to Amsterdam, and from Amsterdam there is the only dynamic part between Amsterdam and Frankfurt, and from Frankfurt there is again a static infrastructure to Karlsruhe. This is a switch which was introduced more at the end of the project. This is a transition switch from 1GE infrastructure to a 10GE infrastructure, and then the interfaces of the MCCs at Frankfurt at the GEANT MCC, one the production MCC, and the testbed MCC had to be upgraded as well. Having a quick go through the reservation procedure. So what you need for getting the reservation is getting an account for logging in, then specifying the home domain. This list there is a snapshot currently what there are as possible possible domains. Then the destination domain, the name is inserted from your login up there. Then you have to specify a justification for the reservation and mark at reservation done. Then it brings you up to the next screen. There you have the possibility to specify optional parameters. There, for example, can be specified a different MTU size, or you can specify path constraints, where which path should be included in the reservation and which should be not included in the reservation. But what you have to specify there is the start point at this side and the VLAN ID, the endport, VLAN ID of the endport, and the time zone. Since you specify a start time and the end time, this is about the start and end time is relative, or is then taken to the time zone you specified there, and the capacity, and description again, and add reservation. This will bring you to this screen there. There you can check again if the information you have entered there are correct, and then either if there was something mistaken, then you can say remove reservation, which will bring you back to the first reservation page, or you say submit reservation, and this reservation is then done to the scheduler, and the action there in the beginning will change. This is one error I will highlight, which we had during the AutoKNF project. This arrow line there, the smaller one, the second one is pretty easy to get out, since this is that the reservation was taken out of the scheduler. The first part of the error message was quite hard to distinguish, to get out what the meaning was, and we found out that it was not possible within the testbed or within the dynamic circuit environment to have one GE infrastructure attached to this 10 GE testbed infrastructure. And out of this reason, we had for the previous mentioned 1 GE transition switch in Frankfurt to place for getting a 10 GE interface to the 10 GE testbed infrastructure of GEANT. But after we had this, we could lighten up a dynamic circuit, and after we had the dynamic circuit first time, we thought, well, let's take a look at the round trip time, and we saw there we have 35 milliseconds. If I do a round trip time to between the same host over the general purpose internet, I get 27.4 milliseconds, and the difference what we see there, it's a different destination or the different lengths of the fiber, since the packets over the general purpose research internet goes direct from Frankfurt, Karlsruhe to Frankfurt, from Frankfurt to Copenhagen, and the dynamic circuit goes from Frankfurt to Amsterdam and from Amsterdam to Copenhagen, and this is just the difference in the length what we see there in the round trip time. But then we injected load in the circuit, and as soon as we injected load in the circuit, the round trip time was raising to 84 milliseconds. And this was not fluctuating between 35 and 84. This was pretty constant, 84 milliseconds. And this is not resolved yet. I'll try to get out why. The next was trying to get out the boundary of a reservation. We have the reserved 200 Mbit per second, and we could achieve a throughput of 300 Mbit per second. The explanation is pretty easy. It is a multiple of STM1. What is covering your reservation, your reserved bandwidth or your reserved capacity, and this is today it is on the website of GEANT that it is a multiple of STM1. Then we were looking into the error, CRC error, so if we could find any error. We couldn't find, this was a 24 hours test, and we couldn't find any error during this test period, and we had the error ratio is even lower than specified there, since I couldn't find any error during the uptime of the dynamic circuit. Except one situation where I found an error. This was I dared there to reserve 2 gigabit, even if I have the end infrastructure is only 1 gigabit. The reason why reserving 2 gigabit is I have 1 gigabit stream, and I then send in the opposite direction another gigabit. Gigabit stream, but this was only ramping up to 500 Mbit. If I reserved 1 gigabit for the capacity of the dynamic link, I could achieve only something around 100 to 150 Mbit at the second stream. So this has something, there is probably some relation which is down to the dynamic circuit, and this is not solved yet. This is this is the bidirectional reduced capacity, which is still in pending action. The other thing, what I would like to get an answer to is these 84 millisecond round trip time. Why do I have a load of? Why do I get this long round trip time when I submit a load to the link? Then the current tests what I did so far were with 1500 Mbits or standard MTU size. There I will still do some tests with different MTU sizes. And there is one issue where I want to, I have the agreement with the German tier 1 side, which is collaborating with the LHC project, and NGDF, which is the Scandinavian tier 1 side. I will connect them via a dynamic circuit infrastructure. Last but not least, there was still the idea of getting AutoBAHN and OSCARs together for having a dynamic circuit between Karlsruhe and Fermilab. So as conclusion is the reservation via AutoBAHN client portal is pretty easy. It's as easy as booking your air ticket, and the dynamic infrastructure is as stable as the point-to-point link via a light path infrastructure. One point is if I have troubleshooting, this is currently not so easy, and but there are things in the process, and I'm sure that this will get to a standard activity, troubleshooting dynamic circuit and connecting dynamic circuit infrastructure troubles with standard troubles. Okay, thank you for your time.
Questions? Any questions to the speaker? It's here. There.
Thank you. Perhaps the problem would be buffer bloat, but the question really is, have you asked the PERTs for troubleshooting?
Let's say I had people directly in GEANT, which were responsible for for clearing troubles with their bandwidth on demand testbed. But the issue was we're contacting them, and then they were troubleshooting the dynamic circuit infrastructure, but then it got stuck. Still, the problem was not solved, and it took then again the initiative from our end, from the end customer end, and then go to the so to those people who are then responsible for the static part of the infrastructure. And this is one point where it's maybe that the different troubleshooting parties of GEANT and of the NRANs, that they are talking together. But this was not via the PERT.
Any other questions to the speaker? So I do have one about your future plans. I saw you were extensively testing the portal. Are you going to test also the web services interface? Are you going to develop some kind of applications at the end hosts to utilize the programmable interface to trigger the dynamic reservations from applications directly?
Let's say no, this is not in the framework of the AutoKNF project. What we more envision is that we take the dynamic infrastructure and look if the dynamic infrastructure behaves as we are used from a light path infrastructure. And this is, but if we then have a real projects like the LHC project, which are heavily dependent on file transfer and make really use of this infrastructure. If you see there.
There is one question.
Yeah, I'm Jan Ferrøy from Denmark. What I would ask you is this AutoBAHN, is that purely for interdomain connections, or do you even want to use it inside your domain? do you see any value in having a bandwidth on demand service inside your domain, giving the different institutions the option of creating paths just the same way as the interdomain is supposed to work?
It is not the limitation that AutoBAHN has to be interdomain. AutoBAHN can be the dynamic circuit can run within one domain. Sure, there is definitely no limitation.
No, but do you see a purpose? Are you going to offer it inside your domain?
I would see the purpose for an AutoBAHN or for a dynamic circuit there, where you currently we see more people, at least even at our institution, approaching us and say, we need a link between this end and this end, and this is a link within one project, and they need it for a certain period in time. Sure, this can be resolved via layer 3 as well, but if I have then they come again and say, but yeah, we need this link, but we want to have it within a tunnel. And if I have then to build a tunnel, then it is not far off anymore, and say, okay, I give you a point-to-point link between these two ends, and you are done.
If you're going to use bandwidth on demand for anything real life, meaning not just showing that it's possible, then you actually need to have equipment at a lot of premises, because beforehand you don't know which institution is going to use it. So I mean, if we want this to spread and be used internationally, then we actually need to have a lot of points of presence where bandwidth on demand is a possibility. So you need to have the infrastructure in the first place.
Okay, yes, you need a certain infrastructure. This is correct. But what you need at the client side is only that you have the ability for let's say having a virtualized interface, a VLAN interface or something, and to deploy this within the institution itself. I think that's it is not so tremendous difficult, but it's correct. They need, and it I think at the moment this is only and something where if you have a certain small number on players, would say, okay, I want to have this and I want to have this, and it does not scale. If you have it is not that you can like a telephone system talk to everyone. For this you need this environment is not realized yet and not possible at the moment. So if you have people or projects which says we want to talk to each other, and you get a certain number on those projects, then you can have an infrastructure where several of those projects are passing through, and the end point and at the sides the infrastructure which are the common infrastructure of these projects. This will then maybe make it interesting for the different parties to invest and while going through this common infrastructure.
Well, one of my points here is really that we should make it not quite as easy as picking up a phone and making a connection, but almost. I mean, just the same way as we wouldn't buy a router today which didn't support IPv6. That's simply impossible. We just can't take the money out and spend it. So perhaps we should try to figure out what is needed for a standard router, or the equipment we would put at some end site. What is needed for it to provide bandwidth on demand as well as the normal internet we provide for the institution.
Mm.
And if we do that, we in time will have multiple endpoints which actually can be used in the bandwidth on demand. And then I think at some point it will set off.
Yeah. Yeah, sure.
Any questions to the speaker? Yeah.
Just a comment on the last question, the effort for making standards that actually will enable all the different tools used, and maybe in the future, or the dream in any case, to have that the effort is made within the OGF, and it's the NSI effort, and this is currently the protocol that was mentioned that is currently used by bandwidth on demand to make different tools speaking together, that Bruno mentioned, the IDCP, is to be superseded and replaced by the NSI in a quite near future. And the goal of the NSI, I mean, as I understand it, one of the dreams of the NSI team is actually, if we have a standard that's deployed enough on the global scale, then we can go to vendors and ask them to have NSI compatible equipment.
Yeah, thanks. Jean-Louis. Okay.
Thank you very much, Bruno, for your talk. Thank you very much for all of the speakers of this session. Thank you all of you for attending. Before we close officially, I need to make some announcements. Do not forget about the gala dinner today at 8 p.m. Directions will be sent via email. You can check this at the registration desk as well. Also, the lost and found items can be found at the registration desks. Also, please check demos and BOF schedule for today online on the website.